Okay, so as a finishing touch for this unit, we can gather everything we have just said about the information that the Taylor polynomial can give us about the behavior of a function, and we can use all this information to actually graph the function, okay, and sketch its behavior, right? And so for that we need to check 7 points, right? The first one is to check what's the domain, okay, of the function first in order to graph it properly, right? Then the second one, it's useful if we and helpful if we find symmetries, right? So if the function is even, if it's odd, if it's periodic, right? So it says in the first two cases, it's enough to represent the function from positive x because the negative x's are just the symmetry of that, right? And then if we have a periodic function, we just need to represent the function in one of the periods, in one of the intervals, because then we just need to repeat that graphically. There are other symmetries possible, such like that the function is symmetric around vertical axis that's not 0, for instance, and so on. But in general, it's going to be these ones. Okay. Now we need to check where the function is continuous and differentiable in order to see where the function jumps, and when we have these cusps, these things where the function are not differentiable, right? And also useful for detecting extrema, right? Now next, the zeros where the function crosses the x-axis, and so it says these points separate regions where the sign of f remains constant, obviously. Now then we need to check where the function grows and decreases, and so in other words, to find the solutions of f prime equals 0, so that we can find the extrema and the point where it grows and stops growing. Okay. Next, the convexity of the function, so that we can see if the function is concave or convex, right? And that's helpful to plot it. And then from that get also inflection points. Typically we will need the second derivative of f for that, but if the second derivative is 0 at some points, that we if it's always 0, then we will need higher derivatives, as we have seen in the previous video. And then finally we want the asymptotes, right? So are the curves which f approaches when it gets close to some point or to plus minus infinity, right? So we need to check the vertical asymptotes. That's usually when the function diverges at some point x equals a. So it's the limit when x go to, so these are the values of x where such that the limit when x goes to a on the right and on the left is different, and so we have either plus it goes to plus infinity on one side and minus infinity on the other, or just plus infinity, something like that. Okay, the function is divergent at that value a. That's a vertical asymptote, right? Horizontal asymptotes are the limits when align with the limit when x goes to plus or minus infinity of f. Okay, and you get some value L. Okay, it could be different at plus and minus infinity, for instance. You could have this. Okay, and then you have inclined asymptotes, which is where the function grows to be something like a curve, right? So something like a real line. Okay, so you say that y is equal to mx plus b is an asymptote of f when the limit when x goes to plus minus infinity of f divided by x is a constant m. Okay, so that means that when or if you want divided by mx is 1, right? So if you want the difference is that when x gets very large, this function f is asymptotically equivalent to mx, right? So it's growing like a line, right? Like a straight line. Okay, and in order to see, but you could have mx here, you could have f of x here. You want to shift this line so that you get it close to f, and in order to do that, you have to compute the limit when x goes to plus minus infinity of f minus mx, okay? And the difference between these two lines will give you b, which is the intercept of the asymptote that you want to compute, okay? So what it says here, in other words, it means that f of x is equal to mx plus b plus small o of 1 when x goes to plus or minus infinity, okay? Obviously, we can also get other asymptotes, and in general you will have that g is an asymptote of f if when x is very large, if f is g plus small of 1 when x goes to plus or minus infinity, okay? Okay, so having said that, let's go to some examples, right? So let's see this function 3x squared plus x plus 1 divided by x plus 2. Okay, so let's start with the first one. What's the domain? Well, the domain of f is, we have a rational function, right? And we know that rational functions, their domain is R minus the points that make the denominator be 0. In this case, it's minus 2. Okay, so it's the only point where the function is not going to be defined, and we're going to see that there's a vertical asymptote there, right? We can't see any obvious symmetries, right? It's not even, it's not odd, it's not periodic, and it's always going to be, obviously going to be continuous and differentiable everywhere except in the point where it's not defined, so that's fine. So in the domain, right? So let's find, so yeah, that's 2 and 3. Let's find the zeros first. Okay, the zeros are the points that make 3x squared plus x plus 1 equals 0, right? And so yeah, this is actually positive, right? This is 1 minus 12, so no real roots, okay? No real solutions. There are no points in which f crosses the x-axis, so no zeros. Okay, this is a parabola that doesn't touch the x-axis. Now about growth, let's compute the first derivative. The first derivative is going to be x plus 2 squared, and then we have the derivative of this, which is 6x plus 1 times x plus 2 minus, and then we have 3x squared plus x plus 1, right? And if we expand this, we have 6x squared plus 13x, right? Plus 2 minus 3x squared minus x minus 1 divided by x plus 2 squared, or in other words, this is 3x plus 12x plus 1 divided by x plus 2 squared. Now let's see, the derivative is 0 whenever 3x plus 12x, 3x squared plus 12x plus 1 is 0. Okay, and we can find the roots of this. This is x minus 12 plus minus 144 minus 12. Okay, and then we have 6, right? So this is equal to minus 2 plus minus, and then we can get this divided. So this is 144 minus 12 is 132. Which is a multiple of 3, and it's a multiple of 6, right? So this is 6 as 22, right? So this is 22 times 6, right? So this is 22 times 6 divided by 6 squared, 36. Okay, so this is 22 divided by 6, in other words, 11 divided by 3. Okay, so this is the square root of 11 divided by 3, and if you compute this numerically, this is approximately equal to the negative one is going to be minus 3.91, and the positive one is going to be minus 0.0, so very close to 0, right? Let me go back here. Okay, now let's see. So the derivative is going to be, this is a parabola, it's positive parabola, right? So this is going to be positive, f prime is going to be positive if x is smaller than x1 and x is greater than x2, right? And is going to be negative if x is between x1 and x2, right? So we have, let's say, this is increasing up until you get to x, so that this is a maximum, okay? Maximum, and then it's, let's say, this is decreasing up until you get to this, and then after that it increases, so this is a minimum, okay? And then we can compute, let's see, we have a minimum, no zeros, and yeah, actually we don't really need to analyze the concavity because we're going to see it now. We just need to compute what happens at the asymptote, right? So there's the limit when x goes to -2 on the left of f, and this is going to be, let's see, what's the x, well, let me erase this, wait a minute, let's compute the value of the asymptote. So this is the limit when x goes to -2 on the left of f is going to be, let's see, this is going to be, wait, it's 12 minus 2, 10 plus 1, so this is positive, so this is going to be negative, right? So positive divided by, this is going to be negative, approaching 0, so this is going to be minus infinity. The limit when you approach 0 on the right, this is positive and this is positive, so this is plus infinity, okay? So now let me go back here and try to plot this thing. Oh yes, so yeah, and what happens with the limit when x goes to plus minus infinity of f, again, and this function is 3x squared plus x plus 1, so that's the limit when x 3x squared plus x plus 1 divided by x plus 2, and we see that this is going to be the limit of 3x when x goes to plus minus infinity, so it's going to be plus infinity when it goes to plus infinity and minus infinity when it goes to minus infinity, okay? So let's see, an interesting thing is that we can't really find horizontal asymptote, but can we find a vertical asymptote, right? So this is, sorry, an inclined asymptote, okay? So if we have the limit when x goes to, and then plus minus infinity of 3x squared plus x plus 1 divided by x squared plus 2x, this limit is going to be 3 in both cases, so we have it's going to be an inclined asymptote, right? This is going to increase, but just as fast as 3x, right? And now we have to find a limit when x goes to plus minus infinity of f minus 3x, and then in this case what we have is the limit when x goes to plus minus infinity of 3x squared plus x plus 1 minus 3x squared minus 6x divided by x plus 2, right? And so this and this go away, so we have minus 5, sorry, the limit when x goes to plus minus infinity of minus 5x plus 1 divided by x plus 2, and this is going to be minus 5 independently on the of the sign, so we have an inclined asymptote that it's the same in both cases, right? So now we have that, this is an inclined asymptote. Let me see if I can plot this thing. Okay, so let's see. We have that there's a vertical asymptote at -2, right? So we have this. Oops, sorry. Okay, -2. we know that the limit when you go to minus 2 from the right is plus infinity, minus infinity here. There's a 0, and there's no 0, right? But close to 0 you have a minimum, and the value of that function, and so remember that f is 3x squared plus x plus 1 divided by x plus 2, and very close to 0 this is just 1 divided by 2, so almost half. Okay, very close to a half. So let's see, it's a minimum here, for instance, right? And then we have a maximum here at minus 4, for instance, close to minus 4. So this is 16 times 3 is 48, minus 4 is 44, plus 1, 45, divided by minus 2, so it's minus whatever, right? So some point here, and this is minus 3, minus 4, right? Point here. And then we have this line 3x minus 5, and wait, let me just plot it like this. Okay, this is the asymptote. Okay, then 4, we have this value, and so we know that the function is going to be very close to this until it gets to the maximum, and then it starts increasing, right? So you can see that you can see that the concavity, so this is a function that's it's going to be, right, it's going to be concave in the negative, sorry, left of the asymptote, and then it's going to be convex in the, okay, convex on the left of the asymptote, right? So and this is the function 3x minus 5, right? So this is what the function looks like, more or less. Okay, now let's do another example. So another one. So this is f is equal to, and 4x divided by x squared plus 9. Okay, this is an interesting function. So first, the domain is obviously the real line. Okay, the domain of f is R, because this is never going to be equal to 0, and this is an odd function, right? F of minus x is minus 4x x squared plus 9, which is minus f at x. Okay, so this is odd, which is okay. We just need to plot half of the function. Now it is going to be continuous, it's going to be differentiable everywhere. There's only one 0 at 0, right? If it 0 is 0, what happens with the derivative? The derivative is 4x squared plus 36 minus, and then we have 4x times 2x, so 8x squared, right? Divided by x squared plus 9 squared. So this is 36 minus 4x squared divided by x squared plus 9 squared, or in other words, this is 4 times 9 minus x squared. Okay, 4 times 9 minus x squared plus 9 squared. So here we have that the zeros of the derivative are going to be plus and minus 3, right? And so we have that the function is going to be, let's see, going to be positive between 0 and, so f prime is positive between, or let's see, in this interval, in minus 3, 3, and it's going to be negative everywhere else, okay, in minus infinity, minus 3, union 3, infinity, right? So we have, what's it, a minimum at minus 3, right? And then maximum at 3, right? Now what happens with the concavity? We can compute the second derivative, and then this is equal to, let's see, using this formula, minus 8x squared times x squared plus 9 squared, and then we have minus 36 minus 4x squared times 2 x squared plus 9, right? All of this divided by x squared plus 9 to the 4th power. Okay. Now we can get rid of some powers of x squared plus 9, so we have minus x squared times x squared plus 9 minus 36 minus 4x squared times 2, right? If I'm correct. Oh yes, and this is the derivative of this 2x, okay, times 2x. And this is 8x, not 8x squared. 8x. Okay, and divided by x squared plus 9 cube, right? If you operate on this, what you have is 8x cube minus 226, sorry, 16x divided by x squared plus 9 cube, and 216 is a multiple of 8, so this is just 8x that multiplies x squared minus 27 and divided by x squared plus 9 cube. So the changes of concavity are going to be at 0, and then at the square root of 27, which is 3, the square root of 3, right? So this is going to be, let's say, this is going to be positive whenever x is positive and x is greater than 3 square root of 3, right? So positive if x is greater than 3 square root of 3, and because of symmetry reasons, if f is smaller than minus 3, and it's going to be negative. Let's say, no, wait a minute. So this is going to be positive here. It's going to, so convex, right? The function is going to be convex. It's going to be also, yeah, and it's going to be negative if x is between 0 and 3 square root of 2. Okay, this is concave, right? And we don't really need to care about the negative side because it's going to be minus that, right? We don't have any vertical asymptotes, right? Because this is, again, 4x divided by x squared plus 9. This is never going to be 0. And then we have the limit when x goes to infinity on both sides. We have it's equal to 0, right? The limit when x goes to plus minus infinity of f, it's going to be 0. So we have a horizontal asymptote. Okay, so no inclined asymptote, horizontal asymptote in this case. Okay, so let's plot this first part and copy it for the negative side, right? So we have again a maximum at 3. We had set, right? The function at 3 is going to be 12 divided by 9, 18. So 12 divided by 19 is going to be let's see. So it's 12 divided by 18. We divide by 6. This is 2/3, right? So something here, 2/3. Function is 0 at 0. We have multiple here. So it's going to be, remember, concave here, and oops. Okay, concave here, and then at some point that's 3 times the square root of 3. So let's say it's here. Then it becomes convex, right? So this is the inflection point, something like this. And then the same way, because the function is odd, you just need to copy it in the negative side, right? So something like this. Okay, this is f of x somehow. Okay, and that's it.